When one thinks of Albert Einstein and his theory of special relativity, there are a host of associations that can arise. For some, it's things like the weirdness of something called space-time that seems to be able to be warped and bent like taffy in the presence of bizarre objects like infinitely dense black holes. For others, it's the strangeness of seeming paradoxes involving twins who don't move through time in the same way, a topic explored in a recent film. For others, there's time travel, or singularities, or any number of other exotic ideas usually discussed on various self-proclaimed infotainment or edutainment channels featuring snippets of interviews with scientists interspersed with narrated voiceovers done by famously eloquent film and TV actors. All of this, I think, often serves to do little more than muddy the waters and make inaccessible through over-sensationalizing what is a remarkably simple and engaging paper published in the second half of 1905. In this paper, one doesn't find all of the weird, mind-boggling exotica that, in the words of one good friend of mine, sounds like scientists are just making a bunch of stuff up. Instead, there are examples and thought experiments taken from the world of someone living in turn-of-the-century Europe that would seem just like symbols of progress and enlightenment: clocks, trains, and railroad signals. The reason for these examples is because that's what inhabited the world of the Swiss patent clerk who walked past the Bern train station every day on his way to the office, an office that had a good view of the city's clock tower. Each day, he sat down to review the ideas and inventions designed to fit into and move forward the ever more interconnected society, one that relied on electromagnetic signals sent across lines and before too long through air, and used in ever-increasing amounts the electrical engineering technologies the clerk's father had produced that were based on the theories of a Scottish physicist and the designs of a Serbian genius and an American industrial tycoon. Yes, Albert Einstein's paper would upend our understanding of the world, but it was not some arcane piece of scientific literature understandable, as would be later remarked, by less than a dozen savants, but rather it was a work of great accessibility that only asked the reader to suspend the long-held and seemingly obvious belief in absolute space and time. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 50.5, Supplemental. Albert Einstein, A Most Miraculous Year, Special Relativity. When we look at the work Einstein did in 1905, it divides pretty neatly into two chunks. The work on what can broadly be thought of as statistical mechanics as related to atoms, and, in the second half of the year, the reformulation of our understanding of space and time, now known as the theory of special relativity. While Einstein regarded his work on the former, specifically that related to the idea of light quanta, as being revolutionary, it turns out that he's actually far better known for his work in this latter area. Something that turned out to be far more revolutionary, I think, than he seems to have understood, at least at first. We'll get to the surprisingly long story of the development of his ideas related to relativity here in just a moment, but I want to take a bit of time to try to explain why I think that this is such an important shift in thinking. Einstein's reformulation of relativity first in this special case that we'll be discussing here, and then 10 years later, when it is generalized to include all types of motion, affects the thinking of a surprisingly large number of fields. When we consider ideas in navigation, measurement, and synchronicity, the technological impact of the reformulation of space and time has of course been quite substantial. A simple example we've mentioned previously has to do with the GPS systems we all use on our phones, computers, and wearable fitness devices. Surveyors are now able to map the surface of the Earth to within centimeters using relatively inexpensive GPS-enabled technologies, with high-end systems being precise enough to measure at sub-centimeter levels. Additionally, timekeeping devices are able to measure even minute changes due to both local gravitational variations and relative motions, allowing for unprecedented accuracy in determining a number of physical properties related to a location. Beyond this, however, there is a more profound influence in the areas of philosophy. Einstein's work in relativity has fundamentally altered how philosophers think about millennia-old questions, such as what is the nature of space and time, and whether things like change are real, an illusion, or a phenomenon related to perception. As we've discussed in recent episodes, it forced cosmologists to rethink their models of the universe and its origin in ways that were unimaginable at the turn of the 20th century or even at the end of the First World War. Moreover, it is clear that as relativity became better known beyond the journals and conferences of the physicists and astronomers, an effort in which Arthur Eddington was so influential, the idea that no observer has a privileged frame of reference had a significant influence on the development of postmodernism. These ideas have shaped the perspective of the world we live in as it emerged from the colonial period that led up to the First World War, and as Europe struggled to make sense of the aftermath of that shattering conflict. And in that, both the ideas of relativity and Heisenberg's uncertainty principle would find fertile soil in which to grow, and be considered outside of their strictly scientific context. While one can certainly debate whether this broader application of the emerging ideas of modern physics was or is appropriate, it is clear that they did have significant influence on the culture and philosophy of their time. Another point that should be made before diving into the material is that as we move through this narrative, you may find that a lot of the information seems a bit esoteric or hard to grasp, and wonder what the big deal is or why we're even talking about all of this stuff. A lot of people over the years have come to the conclusion that this sort of thing is only for the type of people who sort of, make eccentric fashion choices, or wear pocket protectors, or lack social skills, have bad hair, the stereotype, right? However, as we just mentioned, the consequences of Einstein's work are finding their way into more and more of our everyday life. To be literate in the scientific ideas that shape our modern world, I think it's important to understand the basic ideas that led to a reimagining of the framework that we all, and everything we know, moves through. What we'll try to do here is give you, the listener, both the motivation behind this reformulation, as well as tools to help you think of how Einstein did away with Newton's absolute time, and hence his absolute space, in order to create the idea of space-time that Hermann Minkowski would put forward just a few years after Einstein's 1905 papers. A lot of this rests on elegant but subtle thought experiments and arguments that take a bit of work to wrap one's head around. Therefore, as we go through this material, feel free to pause the podcast and spend a bit of time imagining Einstein's thought experiments and their consequences. If you need a few minutes to process, and by the way, pretty much everyone who's ever worked with relativity theory has needed a bit of time to process from time to time, we'll hang out until you're ready to get back to the story. You can just hit pause, think things over, and then when you're ready to move forward, hit play again. We'll still be here. I have to say, when I was studying this, first as an undergrad and then later as a graduate student, I found that I often had to stop working for a bit just to make sure I understood what was going on as I jumped between things like different reference frames, and I considered clocks and rulers, and otherwise struggled to see how the mathematics I was working with related to the physical universe I found out I experienced only incompletely. Okay, so how do you get to the point where you decide to overturn a fundamental part of the foundational piece of classical physics that not only undergirded the Industrial Revolution and the Enlightenment, but also was accepted by nearly every single physicist in the world at the time? Well, as it turns out, there are a lot of small things that have got to come together in the mind of someone who has a tendency to question authority and seek unifying ideas. In other words, someone like Albert Einstein. In Einstein's own accounting of the story, he seems to trace his first ruminations about this topic to a bicycle ride when he was a student at that sort of cantonal school or high school in Aarau. While riding his bicycle, Einstein began to think of what it might mean to ride along with one of the beams of light that streamed through the branches of the trees that hung over the road into the morning mist. At some point, he imagined that when he reached the speed of the electromagnetic wave that light was, he would end up riding along the crest of the wave, and that the undulation of the fields, both electric and magnetic, would stop or freeze. This, however, would mean that there would be no wave and thus no light. And that was just a contradiction he really struggled with. While he didn't make much progress beyond this point during his high school years, Einstein would say that he would return to this particular thought experiment again and again as time went on, and he returned to the problem of the behavior of light. Now, before we go much further, we also need to restate a bit of the background that we've gone through. For those who have listened to our previous episode on relativity, you've heard a bit of this, but since there may be those of you out there who are tuning into the podcast specifically just to learn a bit more about Einstein, let me restate some of the physics that's gotten us to the point where Einstein is struggling with electromagnetic waves in the first place. And if you'd like, and you haven't had a chance to do so, go back and listen to that episode on relativity. That'll help sort of talk through some of the finer points of the theory. So, in the 1820s and 1830s, a series of discoveries had been made that had shown that there was a deep connection between the physical phenomena of electricity and magnetism. Scientists like Hans Oersted and Michael Faraday had shown that electrical currents could produce magnetic fields, and changing magnetic fields could produce electric currents. In the years between 1861 and 1865, the Scottish physicist James Clerk Maxwell had found a way to encapsulate all of these researches into a grand framework that unified the two phenomena in such a way that they could be represented by just 4 equations that could then be manipulated to show that if one either had a periodically changing electric or periodically changing magnetic field, that periodically changing field would produce a, again, periodically changing field of the other type, and the two would propagate through space as a wave. The theory said that this electromagnetic wave would have a speed of very nearly 300 million meters per second, or 186,000 miles per second if you like using imperial units. Maxwell recognized that this speed was very nearly the same as the speed being measured for visible light, and thus suggested that visible light was actually a manifestation of electromagnetic waves in a very particular range of frequencies that belong to a much larger spectrum. This would be shown to be true by the German physicist Heinrich Hertz, who succeeded in producing the first radio waves and thus verifying Maxwell's hypotheses. Now, when we think of waves, maybe water waves or sound waves, we usually imagine them as moving through a medium, water in the case of water waves, or air in the case of sound. When Maxwell was working through the development of his electromagnetic theory, he assumed that there was a medium of some sort in which vortices could be formed as a way of imagining how the various fields would interact with each other. While he eventually discarded this model in favor of a purely mathematical approach, his colleagues did not abandon the idea of a transmitting medium for the wave. The problem, however, is that no one knew what that medium actually was. In a classical case of what's known as philosophical instrumentalism, many physicists put forward the idea that there was a medium, named ether after the old Aristotelian celestial substance that we've talked about in previous podcast episodes, through which the electromagnetic waves propagated or traveled. Since the waves moved very rapidly, it was thought that the ether had to be really rigid, at least in an electromagnetic sense, since terrestrial materials that were more rigid tended to transmit sound waves with a greater velocity, i.e., sound travels much faster through steel than it does through air. However, since the ether had to be everywhere, given that light could travel through all spaces, it had to be virtually massless and non-interfering, since it produced no drag to slow the Earth down in its orbit around the Sun. Strange stuff indeed. It was a substance that had not been observed, but was thought to exist in only the sense that it was needed to explain the observations made about electromagnetic waves. There was, however, a problem with Maxwell's description of these waves as expressed in his four equations. In really physicsy terms, what happened was they didn't transform correctly according to what was known as Galilean relativity. So let's try to break that down in non-physicsy terms so that we can all get our minds around the idea. Among his work on the motions of objects, Galileo had come up with a set of rules to describe the motions of objects within a reference frame as a way to explain how it might be possible for things to stay at rest on a moving Earth, which of course, at Galileo's time, was a topic of huge debate. In doing this, he noted that if you were on a constantly moving ship and dropped a ball from the crow's nest at the top of the ship's main mast, maybe you're sailing aboard the Odyssey here, we're cruising along through the water at just a constant speed. If you drop the ball, what it would look like to you is that ball would fall straight down the mast and land on the deck directly beneath you. Now, in the absence of any other visual clues that the ship was moving, this result would not actually be able to tell you if the ship was moving or not, because you get exactly the same thing if the ship were standing still. You drop the ball, it falls straight down the mast, it hit the deck directly below where you dropped it. Now, if there were a second vessel, let's say a rowboat, that was stationary, and someone on that rowboat observed the path of the ball, he would say if the ship were moving, the Odyssey were plowing forward through the water at a constant rate, he would say that the ball followed an arc from the top of the mast to the deck that combined the forward motion of the ship, something the ball also possessed when it was released, and the speeding up downward motion of the ball would acquire as it fell. The person on the rowboat would combine these two motions to explain the observations of the person on the ship. Now, Galileo realized that this could be simplified if only motions in one dimension were considered. And so the classic example is to sort of think of two people throwing a baseball on a moving train car. In this thought experiment, we'll say that person 1 is standing on a moving flatbed train car that's traveling with a speed of, say, 20 meters per second to the right with respect to the ground. And then we'll say that person 2 is standing on a second train car on a parallel track that is at rest with respect to the ground. If person 1, that's the person on the moving train car, throws a baseball in the direction of her train car's motion with a speed of 30 meters per second, she will measure the ball's speed as being that number. However, the person on train car number 2 will see the ball moving with a speed that is a linear combination of the train car 1's speed and the ball's speed. To put that in maybe somewhat more understandable terms, the speed observer number 2 sees is 20 meters per second for the train car plus 30 meters per second for the ball for a total of 50 meters per second. And this is known as sort of Galilean relativity or Galilean transforms. Now, there are a couple of important points we have to make here. The first is a little thing that we slipped into our description of our thought experiment of throwing the ball, and that is that we're measuring the motion of our two observers with respect to a third thing, the ground. In this case, we're sort of assuming that the ground is what might be thought of as an absolute reference frame, something at rest against which all other things can be measured with respect to. That's a really consequential bit to just slip in, actually, it turns out, and interestingly enough, Galileo doesn't actually do that. In fact, Galileo makes a specific point that if we took the ground out of the thought experiment, what we would say is that the two train cars are moving with respect to each other, but that we can't really tell if train car number 1 is moving to the right and train car 2 is standing still, or if train car number 1 is standing still and train car number 2 is moving in the other direction or to the left. Or if there's some combination where both the train cars are moving so that it looks like one is moving at 20 meters per second with respect to the other. In other words, the fancy term for this that Galileo would say is that neither reference frame is privileged. The transformation of adding the relative velocities of the train cars to the velocity in the frame of reference train car number 1 to get the velocity of the ball in the reference frame of train car number 2 will still work, whatever the case might be. But at this point, it can now be thought of as being just as likely that the difference in the two observers' observations is due to train car number 2 moving towards a stationary train car number 1 as it is train car number 1 moving towards train car number 2. And that's all a whole lot of words to basically say what really is going on here is you can't tell which train car is actually moving. Could be train car number 1 to the right, could be train car number 2 to the left. Turns out both cases give exactly the same answer, and you can't actually tell which reference frame is the one doing the moving. In fact, Galileo makes the specific point that it's from the observations of velocity, or at least that from the observations of velocity, it's impossible for either observer to tell which frame of reference is in motion. That's what makes his discussion of relativity so important in his arguments that it was just as likely that the Earth was moving around the Sun as it was that the Sun be moving around the Earth. What's interesting is that in so far as I've been able to find, Galileo doesn't seem to ever really mention any sort of absolute reference frame in his writings. While it's certainly possible, perhaps even probable given his religious beliefs, that he did believe that there was an absolute reference frame, it wasn't really all that important in terms of his discussions on motion. Instead, the idea of an absolute reference frame comes from the writings of Isaac Newton, who explicitly states that such an absolute and privileged reference frame must exist, and argues rather vociferously with his critics regarding it. While he doesn't explicitly say what defines this reference frame, he just describes that God creates one. He does suggest that it might be defined in some way by the position of stars. Now, the second thing we have to note here is how all of this might relate to light. Light, as we have said, has a finite speed. So what happens when two observers in reference frames that move with respect to each other observe each other's, projection of a beam of light? One would certainly expect that the observer who projects the light would measure its light speed at being 300 million meters per second. But what about the other observer? If the two frames of reference were traveling towards each other, wouldn't the speed of light be greater, using that idea of a Galilean transform we just talked about with reference to throwing a baseball on a train car? Or what if one frame of reference were catching up to the other? Would the light in that second frame of reference now be measured as traveling slower than 300 million meters per second? What if the second observer's reference frame was traveling at the speed of light in the same direction as the first? Would the light beams seem to freeze along with the rest of the world? This, of course, is what Einstein's question was when he was riding his bicycle, thinking about traveling at the speed of light. And these are all questions that really lend themselves to having to sort of yield only to very subtle thinking. So at this point, we've considered like 3 different kinds of thought experiments and Maxwell and Galileo and a whole lot of other stuff. And so probably we need to take just a break, let our brains cool off a little bit, catch our breath, and then jump back into it. So I'll see you here on the other side of the music. Alright, so let's see if we can jump out of the science for just a bit and into some of the biographical narrative information that ties Einstein into these questions. As Einstein's education, both formal and self-directed, continued, he began to realize that there were additional inconsistencies to be found as he thought about light. Probably the first of these had to do with a fundamental asymmetry in Maxwell's equations and how they explained certain phenomena. As we mentioned, one of the things deeply embedded into those 4 equations of Maxwell's was the idea, or is the idea, that an electrical current can create a magnetic field, the idea behind a magnetic coil or electromagnet, and also that a changing magnetic field can create or induce, as it's called, an electrical current in a wire, something that can give rise to electrical generators. The application of these equations and the theory behind them are what gave rise to the entire technology of generating and transmitting electrical power as developed by a number of different inventors and innovators, including Nikola Tesla. It is in considering this second phenomenon encapsulated in one of Maxwell's equations known as Faraday's law, that we find a puzzling asymmetry, or kind of a place where things aren't balanced the way you would expect them to be. Now, here in a couple of weeks, my physics students will conduct a nifty little experiment where they will hook up a simple coil of wire, think of, wire wrapped several times around sort of in a loop, and they'll hook that up to a meter that measures the flow of current. That meter is actually called a galvanometer in fancy terms, which sounds so cool, right? You'd expect to see one of those in Dr. Frankenstein's lab. Well, then what they're going to do is they're going to take a bar magnet, and they would take that bar magnet. It's going to have a north end and a south end, just as you'd expect, and they're going to move the north end of the magnet towards the coil. Now, spoiler alert here, if you want to do this on your own, you probably ought to turn the podcast off and, go try this on your own to see what happens. But if you don't want to wait, what I'll tell you here is what they're going to observe will be a deflection of the needle of the galvanometer, and that will tell them that there is current flowing in the wire as long as that magnet moves towards the coil. As soon as the magnet stops moving, the needle on the galvanometer goes back to zero, and there's no current in the coil. And by the way, the direction the needle deflects, and it turns out it can deflect either positive or negative, that needle will deflect in a very specific direction. And when they pull the north end away from the loop, in other words, they push the north end towards the loop, now they're going to pull that north end away from the loop, the galvanometer actually deflects in the opposite direction. And I guess, if you want to try this at home, something that you can do as long as you can find some sort of a galvanometer kind of thing to hook your coil up to. Now, they will actually repeat these observations, but instead of moving the magnet, what they're going to do the second time is they're actually going to move the coil towards and away from the magnet, and it turns out it gives them the same results as in the first case. When the magnet and coil get closer together, the needle on the galvanometer deflects one way, and then when the magnet and the coil get farther apart, the needle in the galvanometer deflects the opposite direction. As indicated by the name of the law, this phenomenon was had first been observed and analyzed by the British natural philosopher Michael Faraday. After Maxwell's work in unifying electrical and magnetic phenomena, there had been an attempt to explain this particular observation, but that explanation actually turned out to depend on which object was actually moving. In the case of the moving magnet, the common interpretation in the 1890s was that the motion of the magnet through the ether would create an electric field that would then act on the electric charge contained in the metal of the coil, causing the charge to move, thus generating a current. However, if the coil were the thing being moved, then what would happen here is the current would be caused by what was known as a Lorentz force, which was the force of a magnetic field on a moving charge that caused that charge to move. Both explanations produce the observed current, but they suffer from a specific flaw. They violate Galilean relativity. As we said in the first part of this show, one of the fundamental tenets of Galilean relativity is that the laws of physics, which in Galileo's case had just meant the laws of motion, those laws of physics must remain the same regardless of whether the reference frame is at rest or moving with a constant velocity. In other words, there should be no difference in explanations depending on whether the frame of reference is at rest or if it's moving. In the case of our induced current in the coil, that's not what's going on here, at least in terms of the explanations of how the current is being generated in the coil. In other words, Maxwell's equations seem to violate Galilean relativity, which is kind of a problem. Einstein had been aware of this contradiction since at least the time of him having fled Munich and the gymnasium there. As part of his reading to prepare for the admission exam at the Zurich Polytechnic, he had read August Ferpel's 1894 book, Introduction to Maxwell's Theory of Electricity, which had a section that specifically was devoted to the electrodynamics of moving conductors. In this section, Ferpel specifically asked the question as to whether there should be a distinction in terms of the explanation based on which thing was actually moving, the magnet or the coil. The contradiction between the idea that only the relative motion should matter and the different explanations based on what was moving was discussed by Ferpel, and that discussion was specifically mentioned by Einstein as something that continued to capture his attention. However, it's likely that even prior to this exposure to the formal theory, presented in mathematical detail, Einstein was likely considering the problem at least at some level. In that series of books on science written by Bernstein that had so captivated Einstein as a youth, the question is actually something that comes up, and it may well have been a contributing factor to his speculation about the nature of electromagnetic waves from the seat of his bicycle. So, too, may have been the work that he did in his father's and uncle's business, both before and after college, wherein he worked with the physical technologies that use changing magnetic fields to produce electrical currents. This would have been especially true in that roughly 2-year period between his graduation from the Polytechnique and the taking of the position at the patent office, where his knowledge of the theory would have been full-fledged enough that he would have seen the contradictions more starkly. Stepping back for a moment to consider his time in Zurich as a student, we have a letter he wrote to Mileva in 1899 wherein he discusses a key idea regarding these explanations, and that is the idea of this ubiquitous ether. He wrote, quote, "The introduction of the term ether into the theories of electricity has led to the conception of a medium whose motion can be described without, I believe, being able to ascribe physical meaning to it." End quote. In other words, what he saw was that the ether was being used as a de facto absolute reference frame for all measurements and explanations, including the propagation of light. This was despite the fact that no one had actually measured the existence of the ether or what moving through it would do in any of the observations. Over that summer, he tried to work out a way to make such measurements with one of his former teachers in Aarau, but when he returned in the fall to Zurich and explained his ideas to Weber, his teacher there, his professor there at the Polytechnique, the older professor explained that not only was the idea impractical, but that others had already done much of that work. Weber then likely recommended that Einstein read a recent review of the article that had been written by the physicist Wilhelm Wien that recounted 13 previous attempts to measure motion through the ether and its effect on the measurement of the speed of light, all of which had been failures. The most notable of these were experiments by Michelson and Morley at the University of Chicago in 1887 using an instrument known as an interferometer to try and detect the effect of the Earth's motion through the ether. A second experiment had been done by the French physicist Hippolyte Fizeau, whose approach was to try to determine the difference in the speed of light between a beam of light shown through a stationary pool of water compared to light that traveled in a moving stream of water. In each of the 13 cases, Vane explained that there was no difference in the speed of light that had been measured, and there was no evidence for the existence of the ether, at least in terms of a detection. Now, it turns out that the Michelson-Morley result was the most consequential because it seemed to rule out this idea of a stationary ether altogether. However, in the few years following the publication of the result, the Dutch theoretical physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently came up with a possible explanation for that result. Each worked out that if an object contracted by an amount related to the object's motion through the ether in the direction of that motion, the change in the measured velocity of light that should have been seen if the ether were there would actually become undetectable. In a sense, it would be canceled out. In other words, since the measuring instruments being used by Michelson and Morley in one case and Fizeau in the other would be shortened or contracted in the direction of the motion, they wouldn't actually detect the change in the speed of light due to either the motion of the Earth or the motion of water. To be honest, it was really a pretty post hoc kind of a solution, but it did save the idea of the ether as a medium through which light waves traveled, and so it was kind of accepted, at least provisionally, by a number of physicists all across the world. One of the really interesting historical questions was how much these various experiments, most notably that of Michelson and Morley, influenced Einstein's thinking going into 1905. In his paper on special relativity, Einstein doesn't actually cite anyone's work in this area, which leads one to believe that that work wasn't a major influence or that Einstein just didn't give people credit. However, in various interviews over the years, Einstein gave a number of conflicting statements that ranged from not even having heard of the result, something we know is actually untrue given that he had read the paper given to him by Weber, to that result having been instrumental to his thinking. Now, there's been a good bit of discussion on this topic amongst the history of science community, as well as on some ideas whether he might have taken some of his ideas from Henri Poincaré's work, which is a topic we'll return to later. But I think that the best explanation that we really can come up with all of this is that he did indeed sort of know of the work of the two Americans and the Frenchman, but as he put it in one interview, he just sort of took the whole thing for granted as being just something that was quote-unquote in the air at the time. A lot of different people had tried and failed to make the same sorts of measurements, and so, at least to Einstein, the interferometer work done in Chicago, even though it was really the strongest refutation of the existence of the ether, especially when viewed in hindsight, was just part of a larger understanding of the inadequacy of the existing theory to explain what was actually going on. What is likely the case is that the results created something unexplainable that attracted Einstein's attention, but that he wasn't specifically seeking to address directly when he was trying to work out the problem. The next piece of the puzzle regarding the development of special relativity would grow out of the conversation of Einstein's erstwhile philosophical club, the Olympia Academy. As mentioned a couple of episodes ago, the trio of Einstein, Habeck, and Solovin spent a lot of time reading and discussing the various works of philosophically inclined writers. Probably the most important of these works came from three authors: David Hume, Ernst Mach, and the aforementioned Henri Poincaré. Mach was a physicist whose commitment to the philosophical position of instrumentalism led him to question the reality of any scientific idea or explanation that wasn't directly observable. From this position, Mach recognized that Newton had created both absolute space and time as constructs with little direct evidence to back them up, especially in the case of time. Mach wrote that absolute time was, quote, a useless metaphorical concept, end quote, something that, quote, cannot be produced in experience, end quote. Poincaré would add to this skepticism about time in his work, Science and Hypothesis, by writing, quote, not only do we have no direct intuition of the equality of two times, we do not have one of the simultaneity of two events occurring in different places, end quote. In other words, what both men were saying was that the idea of absolute time is suspect due to the fact that we have no direct experience with what it is. This, of course, all built on the work of David Hume, whose focus on empirical observations led him to question the reality of anything that couldn't be directly observed, including so-called laws of causality. One of Hume's most influential pieces of work involved what is known as the problem of induction, and the fact that what we often regard as ironclad rules of cause and effect are actually based on repeated experience rather than on some sort of logical deduction. As Einstein would later write, quote, Hume saw clearly that certain concepts, for example, that of causality, cannot be deduced from our perception of experience by logical methods, end quote. Among these concepts that cannot be deduced is time. On this topic, Hume wrote, quote, from the succession of ideas and impressions we form the idea of time. It is not possible for time alone ever to make its appearance, end quote. As was the theme of our episodes on the philosophy of time a while back, it can be said that we never directly experience time, but rather we construct the concept out of the sense that there is sort of a past, a present, and a future. However, if we don't experience time directly, but only through those sort of sensations, then asks Hume, how can we be sure it exists, especially as an absolute construct? And before we move on, there's one other thing we should mention about these philosophical influences. One of the things Mach emphasized in his writings about science was that for a concept to have any validity, the person using the concept has to define it in what might be called an operational sense. In other words, we can't just say that time exists. We have to define what that means in a way that allows us to use it to describe real things. An example of this might be to say that time is the duration between two events that is measured by comparing each event to some other event or series of events. If I tell you that I watched an episode of Big Bang Theory last night beginning at 7 p.m., what I really mean is that the first instance of that sort of spinning atom graphic that begins the show's lead-in occurred simultaneously to when the bigger hand on my watch face was straight up and the little hand pointed at the 7. If I tell you that the episode lasted at half an hour, what I mean is that the end credits ended when the big hand had moved to the straight down position. Mach said that without such an operational definition of what time was, any conversation was at best confusing and, more likely, was actually meaningless. So this all brings us to the point where Einstein has begun working at the patent office, and he has some time to think about things. As we mentioned, his main interest, at least from his few publications prior to and during this time, seems to have been in the area of statistical mechanics. However, this problem of how to think about light never seems to have completely left him, and as he did his work, there would have been a number of reminders of it. As we've mentioned, in his role as a patent application evaluator, he was encouraged, even expected, to question everything about what came across his desk. During this time, he would have evaluated a number of applications related to various electromechanical devices that would have continued to remind him of the asymmetry in explaining magnetically induced electrical currents. This would have fed into another seemingly unrelated set of patents that would have come across his desk as well, those having to do with the idea of synchronizing clocks. One of the big motivators in Swiss society during this time was the idea of getting things to happen efficiently, something the Swiss are still known for. It was an emerging cultural value that an efficient and well-run society was a hallmark of a civilized people, and so, starting in Bern, the Swiss began to work on creating an infrastructure that would sort of act for all of its public services to occur in regular and predictable ways. Among the most important of these things was the idea that business and transportation should be conducted on a standard time kept for the entire nation. To do this, it would thus be necessary to synchronize the clocks, first in the capital of Bern and then throughout the country. In order to do this, there had to be a way to send a signal between clocks that would allow them all to read out the same time. Now, how does one do this? Well, if we use something really basic, one way you can imagine doing it would be to send up some sort of firework that would explode at a great height that would be seen throughout the surrounding countryside from where that firework was launched. The moment the explosion took place, all of the clocks in locations that could see the fireworks go off would start their clocks at 12 midnight. The next night, this would be repeated at the locations furthest out from that original firework launch, and the clocks that could see those would also be started at midnight. This could go on until everybody was on the same time. This, of course, assumes that the flight time for each firework was standard and they all exploded at the same number of seconds after launch, etc. Now, if you're not super concerned about getting things closer than about a minute or so, this kind of an approach probably works pretty well. You could do it with maybe a bell, anything that produced sound. A lot of different ways to do this sort of a thing. However, with the advent of telegraph and then telephone technology, there was a sense that you kind of had to do better than just sort of 1 minute accuracy or 1 minute synchronization. Thus, there were a number of clock synchronization ideas put forth in the years between 1901 and 1904, resulting in some 28 patents being granted, at least according to author Peter Galson. Almost all of these involved the use of some sort of electromagnetic signal that would have traveled at the speed of light, usually through a line of some sort. Hence, as Einstein reviews these patents, the various questions he had struggled with off and on over the previous decade would have been brought forth many, many times. Galison is careful to say that we don't want to overstate the influence of any of these particular patents and the effect that they might have had on Einstein's thinking. But it's pretty clear that having to evaluate the ideas and assess first whether they were technologically feasible, and second, whether or not they would achieve simultaneous clock readings, forced Einstein to think very deeply about the ideas of both electromagnetic waves and this thing we call time. Okay, so with all these pieces in place, let's see if we can determine what happened regarding Einstein's progress towards a solution to these various paradoxes that he seems to have recognized. To understand his solution, we need to recognize something about how Einstein worked out his conclusions, something we've already mentioned in our previous episode with respect to the papers on light quanta and Brownian motion. Sometimes, when you're trying to figure out how nature works, you look at a lot of experimental or observational results, and you try to find patterns in that data. Once you do this, you can create some sort of a hypothetical framework to explain those patterns. In some cases, this framework will use mathematical laws, if you're just coming up with a description without an explanation, while in others, your hypothesis will have an explanation of why the system creates the observed pattern, and you'll call that framework a theory. This sort of approach follows the scientific methodology first put forward by Francis Bacon in the early 1600s and is known as being inductive, in that you're starting from specific instances of a phenomenon and then generalizing what you've determined to apply to all such similar systems more broadly. Another approach that's different than this inductive one is to begin with a set of fundamental ideas, principles, or postulates, and then, using deductive reasoning, if A equals B and B equals C, therefore A equals C, and often you'll actually do this in the form of mathematical derivation, you work out the consequences of those fundamental principles or postulates. These consequences are then compared to what is taking place in nature to see if there's any correspondence between the two. If there is, then it's thought that the underlying principles or axioms must be an accurate or true description of reality. This process is a deductive one, or sometimes it's now called the hypothetico-deductive method. All scientists use some form of both of these, in that in induction, the laws and theories usually use mathematical models that can be manipulated mathematically to predict additional consequences that can be tested, while in the inductive process, greater success is usually achieved if the scientist has some sort of target to work towards in outlining their initial ideas or how to move forward. The real behavior of nature constrains which ideas are thought to be feasible and what paths of deductive investigations are likely to be most fruitful. In the case of Einstein's work, it is clear that he leaned towards the deductive side of this continuum, wherein he puts forward his fundamental principles, derives the various consequences of those principles, and then, as appropriate, he shows how those outcomes are able to explain a number of real-world phenomena. As he wrote in a 1919 essay, quote, "The simplest picture one can form about the creation of an empirical science is along the lines of an inductive method. Individual facts are selected and grouped together so that the laws that connect them become apparent. However, the big advances in scientific knowledge originated in this way only to a small degree. The truly great advances in our understanding of nature originated in a way almost diametrically opposed to induction. The intuitive grasp of the essentials of a large complex of facts leads the scientist to the postulation of a hypothetical basic law or laws. From these laws, he derives his conclusions." End quote. Thus, as we discussed earlier, it's really no surprise that he made the claim that the Michelson-Morley experiments had little bearing on his work, simply because he began not with the idea that the speed of Earth through a supposedly stationary medium, such as the ether, couldn't be measured, but rather from more fundamental principles that, when taken to their conclusion, showed that the existence of the ether wasn't something required by his theory. As he wrote, quote, "I was pretty much convinced of the validity of the principle before I knew of this experiment and its results." End quote. More than this, however, was the conundrum that to try and start with the empirical results led him repeatedly into a seemingly intractable morass of unresolvable contradictions, especially every time he tried to sort out what was going on in terms of electromagnetic induction. Quote, "By and by, I despaired of the possibility of discovering the true laws by means of constructive efforts based on experimentally known facts, he later said. The longer and more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. End quote. So what would this universal formal principle to be? Well, he had a few to choose from. The first was the principle of Galilean relativity, and the idea that there were no privileged reference frames. The laws of physics had to work the same way in all reference frames that moved at a constant rate. That was true for, the motion of objects as well as Maxwell's equations. The solution of Lorentz and Fitzgerald had thrown this out by saying that there were different things going on for reference frames at rest with respect to the ether than there were for reference frames that were moving through it. Einstein would reject that approach from the very beginning. His long-considered thought experiment of riding along with the light wave convinced him that to reject the principle of relativity would lead to completely unphysical results. The next thing he had to think about was how to consider light. And in this, there were two possibilities. The first was that light was emitted from whatever source, kind of like bullets are fired from a gun. In this case, there was no need for the ether since light was made of particles instead of a wave, and the particles didn't need a medium. And by the way, this was something that sort of was supported by his earlier paper on light quanta. The issue with this was that if this kind of an approach were the case, one would think that Galilean relativity would require you to add the velocity of the source that was firing the light bullets or light quanta to the velocity of light itself, much like in our train example. This required that Einstein would have to say that Maxwell's equations were wrong since they produce a description of electromagnetic waves where the speed of light didn't depend on the speed either of the source or the observer. In this emission theory, as it was called, the information about the source's velocity would somehow have to be inscribed in the light itself, something for which there was no evidence. Moreover, no matter how hard he tried, or they tried, I should say, the various experimentalists that were trying to do so couldn't seem to come up with an experiment that showed that the speed of light in a moving reference frame was different than the speed of light in a reference frame that was at rest. The second idea was to say that the speed of light was, in fact, a constant 300 million meters per second in every reference frame that might produce it, something clearly supported by Maxwell's wave equation. This, however, really did seem to violate parts of Galilean relativity, which said that the speed of the wave and the relative speed between the source and the observer should be added together. Because of this, Einstein initially tried to make things work with the emission theory, but the more he struggled with it, as the quote sort of indicated, the worse things became in trying to understand how light interacted with matter. Finally, this led him to abandon the idea and accept that the speed of light had to be the same in all reference frames. While a source moving towards or away the observer would modify the frequency of the light wave in accordance with the Doppler effect, the speed of the wave itself would be unaltered. And this became his second principle. For about a year, starting in 1904, he wrestled with the incompatibility of his two postulates. This contradiction was that according to Galilean relativity, the speed of light should change when measured by an observer moving with respect to the light source, while the principle of relativity said that there should be no way to tell which reference frame was at rest and which was moving, and so the speed of light should be measured as the same value by the two observers in different reference frames moving with respect to each other. By May 1905, he was at wit's end and was ready to give up on the problem when something in a conversation on the walk to the patent office got him unstuck. Einstein had recruited his old friend, Michele Besso, to come and work at the patent office, and the two would often walk to work together right past the Berlin train station with its long row of clocks for those departing the trains to do their business in the cities so that they could set their personal pocket watches to. We don't know what the two talked about specifically, but Einstein later, in a talk that he gave in Tokyo in 1922, related that he had announced that he had basically decided to give up on the problem. In the ensuing conversation, Besso apparently said something that got Einstein to thinking in a completely new way. between that conversation and the two men greeting each other the next morning, Einstein managed or somehow took the big step that allowed him to resolve the conundrum. We don't know what it was that got him to shift his thinking, but given the locale of the train station and the clocks and the thought experiment Einstein would use to explain his breakthrough, I imagine that it might well have had something to do with how to think about the timing of the train schedules. So what was Einstein's big breakthrough? Well, to put it briefly, what he realized was that the contradiction wasn't with the two principles, but rather it was instead with the idea that whether two events actually happened simultaneously was something that was dependent on the motion of the observer. The famous thought experiment that explained this is the two observers on a train embankment observing two flashes of light thought experiment. While I've discussed this in our episode on relativity, let me recap it here as it forms the foundation of just about everything else. In this thought experiment, imagine two observers, one on a moving train and the other on a stationary embankment, or maybe better yet, let's think of that person standing on the train platform. Let's say that the exact instant when the person on the moving train is exactly across from or next to the person on the platform, two signals, equally distant from that point, flash, giving off light that travels towards the observers that are, at that instant, in the exact middle of the two signals. Now, for the observer on the platform, the light emitted from each of the signals that are at rest in his reference frame will take the same amount of time to travel the same distance, and so he will observe them as flashing simultaneously. For the observer on the train, however, while the light is traveling towards that point, the train will move some distance forward, and so the flash from the signal in front of the train will arrive a bit earlier than the one coming from behind the train, due to the former having to travel a shorter distance to get to that observer on the moving train. Hence, the observer on the train will not see the two events as happening at the same time. This means that the two observers will no longer measure time in the same way. The events, how they define simultaneity, will be different. The upshot of this is that Einstein has shown that the solution to the seeming contradiction between his two principles could be resolved by showing that there's really no such thing as absolute time. He would then also go on to show that one can't think of space as being absolute either. Over the course of the 5 weeks between that May conversation at the end and the end of June, he would immerse himself in the work of doing the various sort of calculations and formulations and sort of thinking things through that would result in a paper that would be titled On the Electrodynamics of Moving Bodies. Given what we've discussed, why was the paper given that title? We haven't talked anything about those things, right? Well, actually we have. The reason the paper is given that title is the physical problem Einstein's actually trying to solve is this asymmetry issue in the explanation of how current gets created in a coil of wire when the coil is placed in a changing magnetic field, either due to its motion or due to the motion of a magnet, as we discussed earlier. What Einstein shows is that the assumption that one or the other object is at rest with some stationary medium, such as the ether, is unnecessary and unphysical. Instead, he puts forward his principle of relativity as a postulate, and then his principle that the speed of light is the same in all reference frame based on his first postulate. This then leads to his explanation that time and space are not absolute, and that simultaneity is something defined locally in a specific observer's reference frame. As he would later say, quote, "There is no tick-tock everywhere in the universe that can be considered as time," end quote. This would then lead to the phenomena known as time dilation, where a clock in a reference frame that is moving with respect to an observer will appear to run slower, and length contraction, where a meter stick will appear to be shorter in the direction of motion in that same reference frame. Of course, to the observer in that reference frame, both her clock and meter stick will appear normal, while those that are sitting in the first reference frame, seen from her perspective, now to be moving, will appear to display the same effects. And so Galilean relativity is preserved in that the observers in each reference frame sort of observe the length contraction and the time dilation effects in the other person's reference frame. In terms of the mathematics, the equations Einstein derives are identical to those of Lorentz and Fitzgerald. But in his case, they don't actually describe a mechanical shortening of a physical object in absolute space, but rather a shortening of a non-absolute space as perceived from a specific reference frame. While these results are groundbreaking in their implications, what's interesting is that they aren't what Einstein was actually trying to resolve. They are important results that he found on the way to his final conclusion, but they're not actually the final conclusion itself. That conclusion was actually to show that Maxwell's equations should be reinterpreted in such a way that there was no longer an asymmetry between the two explanations of induced current. Instead of thinking of motion with respect to an ether that was no longer needed, what Einstein was able to show was that when an electric charge moves with respect to a magnetic field, a part of that magnetic field will be transformed into an electric field in the frame of reference of the electric charge, and that it is this electric field that exerts the necessary force on the charge to create a current. And it doesn't actually matter which thing is actually doing the moving, as long as they're moving with respect to each other. This idea that the ether was no longer relevant would also be a fundamental result of Einstein's work here. In a letter he wrote soon after to Sullivan, he said, quote, "The theory of relativity can be outlined in a few words. In contrast to the fact, known since ancient times, that movement is perceivable only as relative movement, physics was based on the notion of absolute movement. The study of light waves had assumed that one state of movement, that of the light-carrying ether, is distinct from all others. All movements of bodies were supposed to be relative to the light-carrying ether, which was the incarnation of absolute rest. But after efforts to discover the privileged state of motion of this hypothetical ether through experiments had failed, it seemed that the problem should be restated. That is what the theory of relativity did. It assumed that there are no privileged physical states of movement and asked what consequences could be drawn from this." End quote. With the period of intense work done and the paper written, Einstein would suffer something of a physical collapse in late June. He was just exhausted from the intensity of the work. During this time, Mileva went over the paper, checking and double-checking the work to make sure there were no obvious errors that would embarrass her husband. Once done, Einstein mailed it to the Analander Physik, and, in one of the very few instances of this happening, he and Mileva celebrated by getting, as I learned to call it when I was a kid, schnockered. On that evening, they wrote to Habeck a coda to the letter that had promised the original 4 papers. It was simply one line. Quote, "Both of us, alas, dead drunk, under the table." End quote. At this point, the episode has begun to reach a length that is a bit longer than I generally like, though we seem to reach it more and more often as of late. Before we close, however, I should mention that Einstein would publish one more paper in 1905. Only about 3 pages long, it serves as something of an appendix to the special relativity paper. The subject of the paper he had again revealed to Habeck in a letter prior to its submission. Quote, "One more consequence of the electrodynamics paper has crossed my mind. Namely, the relativity principle, together with Maxwell's equations, requires that mass be a direct measurement of the energy contained in a body. Light carries mass with it. With the case of radium, there should be a noticeable reduction of mass. The thought is amusing and seductive, but for all I know, the good Lord might be laughing at the whole matter and might have been leading me up the garden path." End quote. This paper, titled "Does the Inertia of a Body Depend on Its Energy Content?" contains within it the most recognizable equation in physics, E equals mc squared. Using only 3 equations to describe a system of 2 light pulses emitted in opposite directions, Einstein was able to show that mass and energy are equivalent manifestations in a way that even those working with cathode rays and radium salts in the laboratories of Cambridge and Paris had failed to fully appreciate. There are, of course, a number of questions we've sort of left unanswered in this episode. Among these are what were the influences of others such as Lorentz and Poincaré, who could be said to have been moving in this same direction as Einstein, and whose work Einstein seems to have drawn from. Additionally, what role did Mileva play in the development of relativity? Also, given the profoundly revolutionary nature of two of Einstein's 1905 publications, how were his ideas received by the larger physics community? We'll try to get at answers to all of this, as well as discuss Einstein's journey from the patent office to a full professorship in Berlin over the course of the following decade in our next episode. As we wrap up here, I'd like to take a moment to recognize the passing of Stephen Hawking. Hawking was both a brilliant physicist who did work at the intersection of particle physics and cosmology, and whose insights have been just absolutely instrumental in guiding a generation of work in both fields, as well as being a popularizer of science. Like many of my generation, his A Brief History of Time was one of my early introductions to many of the ideas of cosmology, and I'm not ashamed to admit that, like literally everyone else I've ever talked to, I got lost while reading the book. I can't tell you the number of times I've been chatting with somebody about A Brief History of Time, and the story comes up where they relate the experience that they were moving through the book and things were kind of making sense and it was going reasonably well, and then they turn a page and all of a sudden nothing makes sense. In fact, in grad school, the question wasn't whether that had happened, because it had happened to all of us, but instead just how far into the book had we gotten before that had happened. Fortunately, Hawking's other popular works were written to be a lot more accessible, and you don't hear stories about the other ones quite in the same way. While I don't actually very much agree with a number of his comments regarding the relationship between philosophy and science, I do think we're all indebted to his insight and inquiry into some of nature's deepest mysteries, and I personally am really thankful for the fact that he seems to have had a great sense of humor. I also want to say thanks to everyone who over the last few weeks have taken a few moments to drop me a note either via my email or through Twitter. I just really do appreciate your words of encouragement and appreciation. It's always nice to know that what I'm producing here is of value to you all, and I want you to know that I'll keep working to try to bring you high quality information and narrative. If you have any suggestions or just want to say hi, you can drop me a note at cldavies@mac.com, find me at Twitter, @ChadDavies is my handle, or join the podcast Facebook group, though given the recent revelations about that particular platform, I can understand why you may not be there anymore. I also want to thank the folks at the Blue Dot Sessions for so generously allowing me to use their compositions here. If you'd like to hear more, I'd really recommend heading over to their website, sessions.blue. Lastly, before we sign off, I want to put in a plug, for another show, the Skeptoid Podcast. Brian Dunning really puts out a good program that I think a lot of you might like. Just as importantly, his organization, Skeptoid Media, has produced a YouTube video called Principles of Curiosity that does a great job of talking about critical thinking. I use it in my colloquium course at the college I teach at that I actually have for teaching scientific inquiry. I know that many of those of you who do teach will find it a wonderful resource. He's also working to raise some money to produce a show that examines the sometimes not so great intersection between science and scientists and the media that he's titled Science Friction. If this sounds like something you might be interested in supporting, head over to the Skeptoid Media website to find out more. Next time on the podcast, we'll take a look at Einstein's angels. Until then, full sails on your journey.